Hi, welcome to the Chapter 2 presentation. Chapter 2 involves atoms and the periodic table. There is a handout to accompany this presentation, and so please check out Moodle to find that particular handout. The PowerPoint presentation is also there. You may want to pick out which slides you want to print if you decide to print anything, because some of them have jokes in them that you might as well save some ink and paper not printing out. I'm going to go ahead and get this started with y'all now. In Chapter 2, we will talk some more about elements and the atoms that make up those elements and how we have them all in a handy-dandy periodic table like the one I have on my wall, because I'm just that cool that I have a periodic table on my wall. I know you're jealous. You too can have one if you search online for a shower curtain periodic table. As a reminder, from Chapter 1, we learned that elements are pure substances that cannot be broken down into simpler substances by a chemical reaction. Compounds can. Those can be broken down into individual elements by a chemical reaction. But with elements, no physical separation, no filtration or evaporation, anything like that's going to work. And chemical reactions will not work either. We can do really fancy experiments to look inside of atoms of each of these elements, but I can't break them down into something new by a chemical reaction. Each element is identified by a 1 or 2 letter symbol. Some you may already know, such as O for oxygen and C for carbon. And then there's some, say, Mg for magnesium. Those are some typical symbols that we would find for our elements. Then the elements get arranged in the periodic table of elements. And it's a really, really useful thing because where an element is on the periodic table tells us a lot about its chemical properties. And remember, chemical properties let us know how one substance will react with other substances, or in this case, how an element will react with other elements. Here's the classic one where we have different shades. I believe this is the one where I gave you a link to it online because I thought it was nice. What I like about it is that it gives you the names and what we call the atomic masses, which we'll talk about more. They're all on here. I also like the numbering system. It has the traditional numbering with Roman numeral 1, Roman numeral 2, and across with Roman numerals, but it's also using the more modern version where we work with 1A, 2A, 3A, and so forth. And down in the middle, it works with 1B and 2B, things like that. The colors will also help. They classify different categories. For example, if something is a metal or a non-metal, all of those are colored in for you. We'll be referring to this a lot in, well, at least throughout the general chemistry stuff and some past that. Atoms and the periodic table with these elements, it will honestly be a lot easier for you if you memorize the symbol for some of the basic elements. And the first 20 elements will be the ones we use the most. That would be hydrogen, he's element number 1, helium number 2, lithium, beryllium, and so forth. The last one in that category, then, number 20, would be calcium. If you go ahead and memorize these formulas, it'll be handy for you. Let me give you a fun place to go to help you with some of these. I'm going to escape out of this PowerPoint, and I'm going to go over to freerice.org. Free or freerice.com, both of them, it'll take you there. This is a neat website because it gives you essentially practice quizzes, but When were you born? Okay, this could take a while. Didn't have to do this before. Okay, hang on. I'm going to pause the recording for a second. Okay, and apparently chemistry is being highlighted today. We have the chemical symbols, the basic ones, and the list of different choices are here under categories. The new categories that you might learn, wow, you can learn about ancient Rome, Japanese vocabulary, and then there's practice with English vocabulary, English grammar. With geography, I practiced geography because I moved every year in school, so I missed geography in school. I practiced doing famous paintings before, so learned a lot about that, and been practicing Spanish on here as well. And sometimes just to review my French, I'll go on here as well. But if we keep scrolling down, wow, there's a new thing on coronavirus. Currently, we're on chemical symbols basic, and these are all you might want to know. If you decide to get kind of frisky with it and really push yourself, you could do chemical symbols full. Why am I sending you to this site? Well, every time you get a correct answer, it's another grain, 10 grains of rice. And then when you get up to 100 grams of rice, that's essentially a new bowl of rice for someone. And if we check out what this is about, do they have a thing about, there it is. They change which organizations they're giving food to for a while. As you play and get the answers correct, you will see advertisements, but thanks to the advertisements, you are triggering a financial payment to the World Food Program to support its work, saving and changing lives around the world. And it's represented with grains of rice, and they're going to keep purchasing rice. Oh man, it's down to 5 grains of rice instead of 10 because the online market's not getting enough money. Every little bit counts though, right? So come on over here to practice memorizing your different chemical symbols, and that will make it easier throughout the semester if you have the basic ones memorized. But you'll always have a periodic table, either this one or the one online, which you are allowed to go to during a test, or you might print out the one I gave you, and then when we were in class, I would pass out colored pencils and people could color in the different sections on the periodic tables. So that might be a fun activity for you to do once you know some more about the different categories. I'm going to get rid of this black box on my screen, and let's take a look at what else. Then above number 20, there are still another 3, 6, 12 more that we use fairly often that you might want to go ahead and memorize. I don't see uranium on here. Uranium's going to come up probably a little bit, and a few other ones when we do the next chapter, which will be chapter 10, when we do nuclear chemistry. In nuclear chemistry, you'll learn how we can change from one element to another, but that's very different than a chemical reaction. Oh, little tricks. So to help you with memorizing, if someone takes my gold necklace, I say, "Hey, you, bring me back my gold." But if they take my silver necklace, I'm like, "Ag." And then if they take a copper item, it's just like, "Oh, see you later." So that helps me remember my AU, AG, and CU. Of course, lead, very dense. You know how it goes, just like peanut butter, very dense when I'm trying to swallow my peanut butter into my stomach. And oh, statin, so SN for tin. I think of statin all over the place. And how cool is it that there's a Krypton, the planet that Superman's from? That obviously they had some inspiration from the element Krypton. Anything else in here? Nope, those are the ones that I have some fun with remembering their symbols. How often do you like jokes about elements? Periodically. Of course, for me, it's probably more often than your periodically is. There are 3 classes of elements. There's metals, and the majority of elements are metals. Look at all this stuff. starting on the left-hand side, all the way through the center, even creeping over a little bit to this right-hand side, plus the two lower levels that didn't quite fit for the symmetry of the periodic table. They were pushed down below. All of those are metals. Then separating the metals from the non-metals are the metalloids, which to me just sounds like robots, futuristic robots. And in fact, some of the metalloids are things like silicon, which ends up in robots and computers and calculators. So maybe it's purposely sounding a little bit robotic. My non-metals are all over here on the right-hand side, and poor little hydrogen over on the left. He's a non-metal, but he's over there for different reasons with chemical properties. That's part of why he's over there on the left-hand side. Some periodic tables will show him over on the right-hand side above that number 17 there, just to show that he's part of the non-metal group. We have these elements divided into three groups, and the properties of the metals. Well, first of all, they're located on the left side and middle of the periodic table. They usually exist as shiny solids at room temperature. So that's important, that almost every metal is a solid at room temperature, except for mercury. Mercury is a silvery liquid at room temperature. I used to play with mercury as a kid. It came in a game called Quicksilver, and it was a little maze that you had to take the liquid mercury through to get to the end. Of course, now we know that the fumes that come off of mercury are toxic, which is probably part of why I am the way I am. But it is a fun element to play with if it can do it safely. The other thing about metals, as you well know from cooking and the copper wires that we use in our homes, they are good conductors of heat and electricity. What that means is that if I put heat on one end of it, I'll start to feel heat on the other side because it allows the heat to travel through the particular solid that we're heating. And same with electricity. If I have a source of electricity at one end, then it travels through to the other side. That's being a good conductor. For my nonmetals, they're located, as I showed you, on the right side of the periodic table, except for hydrogen. These guys usually do not have a shiny appearance. They're usually poor conductors of heat and electricity. And they can be solids, liquids, or gases at a room temperature. And I want you to be careful with this because a lot of the nonmetals are gases, but not all of them. People automatically assume that all nonmetals are gases, but that's not true. Of course, I don't have any carbon on me right now. A diamond made from carbon, that's not a gas. The carbon that's in our graphite pencils, the pencil lead, it's not really lead, it's carbon. That's not a gas. So keep that in mind. Here's some to let you know. So carbon, sulfur is another example of a solid nonmetal. The only other element out of all the elements we know so far that, well, stick around long enough to know their properties, we have the liquid mercury at room temperature and liquid bromine at room temperature. Gases, nitrogen and oxygen are a couple of examples of nonmetal gases. Hydrogen, again, is a nonmetal, even though it's usually found on the left side of the periodic table. And that has to do with how many electrons. Well, he has one electron, and how he reacts with other elements. Lastly, our metalloids. They're located on this solid line that starts at boron and angles down toward astatine. On the printable version of the periodic table, I created a zigzag line on there so that you could see which ones were there. I'm going to pause recording and go have some dinner, and when I come back, we can look at this again. And I'm back. It's a delicious dinner. I love my roommate. Does a great job cooking and lets me eat it. So, back to work. Our metalloids are located on the solid line that starts at boron and angles down toward astatine. Let's see if I can go backwards with this and you can take a look, or just look at the one that I have posted on Moodle or the one that you might find online. It's a zigzag situation. And the metalloids have properties that are intermediate between metals and nonmetals. In fact, some of them are known as semi-metals. They're represented by only 7 elements, and those are boron, silicon, the one that's in the electronics, germanium, arsenic, antimony, tellurium, and astatine. Now, if you guys didn't have access to certain periodic tables and everything, I'd give you some tricks for remembering it, but I think you're going to be just fine. We're going to go over some new physical property terminology. Some of this is in the textbook, but it's also stuff we need to know for lab. Whoa, it all comes up at once too. The luster. Luster is defined as something with reflecting light. So things that are shiny or glossy, those have luster. Ductile. Ductile is being able to be stretched into the shape of a wire without breaking. Copper, for example, is famous for being ductile because we often see it as copper wire. Malleable. Malleable objects are able to be shaped into a thin sheet by hammering or rolling. Aluminum foil is an excellent example of this. You can also have malleable people who are easy to persuade to do things. And you might also think of Play-Doh as being that stuff that kids work with that's kind of a very soft clay. That's the idea of malleable. And then we talked about conductors, a material or device that conducts or transmits, allows to pass through it, heat, electricity, or sound. And so here we have copper, another page that you would not want to print out, saying, hi, I'm copper and I'm a metal. Some of my favorite pastimes include being malleable, ductile, shiny, and solid at room temperature. I also enjoy conducting electricity and heat. Call me, because, copper wires and the phones. Yeah, that's kind of old school, landline kind of humor. And then there's sulfur. Hello, my name is sulfur. Like my friend copper, I work on the periodic table. However, I am a non-metal. Copper and I could not be more different. I take pride in being brittle. Brittle means that it easily crumbles like a cookie. And dull, not shiny. Maybe boring too, I don't know, but in this case, dull meaning not shiny like a metal. I am not ductile, cannot be pulled into wires, and I can't conduct heat or electricity. Very much like we see with carbon as well. And then that gorgeous silicon, I showed you guys some pieces of it in the lab video that I made because I think it's so cool. It really does look like this. And I wish I could do a Australian accent, but I'll give it a try. Hello, mate. Metalloid silicon here. Some may say that I'm wishy-washy. Sometimes I act like a metal. Sometimes I act like a non-metal. For example, like a true metal, I am ductile while heated. But at room temperature, I'm as brittle as an old lady's bones. So there you go. I did give up on that accent for your sake. And definitely a mixture of properties then that depend on the temperature. I want you guys to be familiar with the elements of life. And so living organisms, you should know, are selective about which elements they absorb from their surroundings. 96% of the mass in the human body is made up of only 4 elements, known as the building block elements. They include carbon, hydrogen, oxygen, and nitrogen. Now, 2 of those are not surprising. The hydrogen and oxygen make up water, and that's the main substance in our bodies. Carbon, hydrogen, and oxygen are found in all 4 main types of biological molecules. That's your proteins, carbohydrates like sugars and starches, lipids, Those are fats, oils, some of the steroids, and nucleic acids. All contain carbon, hydrogen, and oxygen. Nitrogen is also found in proteins and nucleic acids, DNA and RNA. And when we don't have, if we eliminate the water from our mass, then the next greatest mass in our bodies is proteins. So there can still be a lot of nitrogen in our bodies as well. 7 other elements are also present in the body in much smaller amounts. Those 7 elements are known as major minerals or macronutrients. We're going to get these minerals from our diets. You don't have to memorize any of these, but here are our major minerals. Things like potassium, sodium, chlorine, magnesium, sulfur, calcium, and phosphorus are found throughout our bodies. Many other elements occur in very small amounts. These are known as trace elements or micronutrients. They're still essential to good health, and we still have to get them from our diets. So this is why having a healthy diet is so important. Some of those are kind of cool. Arsenic, which in high concentrations can kill you. And what's another one? Of course, fluorine we're used to. Iodine, our thyroid glands need iodine to function. Molybdenum, that long word there, molybdenum. It's a metal that I used for my dissertation in graduate school. We were making organic molecules using this transition metal, molybdenum, to help with forming stuff that might not form otherwise. Atoms. All right, so we've been talking about elements, and atoms make up elements. Let's see what they are. They're the basic building blocks of matter. John Dalton. I don't make you memorize, or I won't make you memorize this one either, but I don't talk a lot about different chemists. In some courses, they focus a lot more on that. But John Dalton was a pretty cool guy because he was the scientist who proposed the idea that elements are made up of particles called atoms. Now, he wasn't the first one. There was a Greek philosopher named Democritus who way back in the time when Aristotle was around. So we're talking, I don't know, BC sometime, maybe 100 BC or BCE, before the current era. Aristotle said everything was as you see it, that's what it was. So a rock was just a rock, nothing smaller than what you saw. But Democritus said, no, there's littler particles making up that rock. And everybody believed Aristotle. And so for the next 1 or 2,000, like 1,800 years or whatever, his idea ruled that nothing was broken down into smaller parts. Then John Dalton and some other scientists come along and they do some experiments and say, wait, no, he was right. These different objects are made up of different types of atoms, these building blocks of matter. Each element is made up of only one kind of atom. For example, the element hydrogen is made up of only hydrogen atoms. I didn't wear my t-shirt that I wore last time that said, never trust an atom, they make up everything. Well, that still plays a role in this then. This gold bar shown above could be broken down into tiny pieces until all that were left were those tiny little spheres there of gold that could no longer be divided. Those indivisible, not capable of being divided, those indivisible parts are called atoms. Even the most powerful light microscopes we have today cannot see individual atoms. All matter is made up of different combinations of atoms. For example, 1 oxygen atom and 2 hydrogen atoms can combine to form the compound water, good old H2O. But if 2 oxygen atoms combine with 2 hydrogen atoms, then a new compound is formed, hydrogen peroxide, H2O2. Even though there are countless different substances in the universe, there are only about 100 different kinds of atoms that are the building blocks for all of them. about 92 elements so far have made up all the known matter in the universe. Now, I'm not talking about antimatter or anything like that, but just the matter that we can touch that has mass and takes up space. That matter is made up of about 92 different elements, and that's it. Did I surprise you? I love that I have a really crappy memory because that surprises me every time I come across it. Okay, so here we go. Compounds and chemical formulas. A compound, as we saw in chapter 1, is pure. Oh, I turned off my thing. One sec. So sorry about that. I thought about restarting the video, but at this point, I think we've been working on it long enough that I'd rather just keep going. Where were we? I was telling you about the compounds like sodium chloride or water, H2O, being pure substances formed by chemically combining 2 or more elements together. We can look at them with a chemical formula. That formula contains the element symbols to show the identity of the elements forming the compound. So the H and the O in H2O. The subscripts will show the ratio of atoms in the compound. If I have H2O, that's telling me 2 hydrogens for 1 oxygen. Ah, there you go. So the subscript is the little 2. There's also an invisible 1 to the bottom right of the oxygen atom. But the fact that he's written there with no subscript that's visible tells me there's 1 of it. How about with C3H8? How many carbon atoms are there? And how many hydrogen atoms? I'm going to play Dora the Explorer and say, yes, you are correct. It is 3 carbon atoms and 8 hydrogen atoms. How about SiCl4? Now you may take a second and check your periodic table. Si is for silicon. Cl, all the way on the right-hand side, pretty close to silicon, that's chlorine. So this has 1 silicon atom and 4 chlorine atoms. I'm going to give you some chemical formula and spelling tips at this point. They're not in your book. This is me trying to help you. First of all, chemical formulas are also known as molecular formulas. So if I'm asked for the formula of a compound, I know to put, or a molecule, something like that, it's going to be H2O, for example. Each capital letter, each uppercase letter, that's another element. Just like I did in the previous example, when I saw C with a straight line next to it, I assumed it was chlorine. C with an I next to it, carbon and iodine, those are rarely seen together. Nowhere near as often as I'm going to see a Cl standing for chlorine. We'll see chlorine a lot, not so much C and I bonded together. Spelling tricks. When you want to spell fluorine, just remember that fluorine has the flu, or maybe it's just faking. So, fluor. Chlorine and chromium are either, you could say, on the choo-choo train, or they choose to keep the H silent, something to help you remember that even though the symbol is Cl, it's still chlorine. And even though the symbol for chromium is Cr, it's still CH. Chlorine is CH. Phosphorus likes to shop at Toys R Us, which just kind of makes me sad now because, of course, Toys R Us went out of business. I don't know where phosphorus shops any longer, but RUS is what helps me remember how to spell the end of it. And finally, sulfur. Sulfur, UR, a really useful element. So that helps me remember it ends with UR and not ER. You may see compounds like sulfur spelled with a PH instead of an F. That is the English spelling, or ones that the British people use. Compounds can be drawn in many ways. You saw some of this back in chapter 1, where you were looking at images to tell the difference between a solid, liquid, and gas, between just one element, just one compound, or a mixture of those. We have the chemical formula or molecular formula, H2O, the ball and stick representation. This is designed to show me two colored spheres to represent the hydrogen atoms. The stick between them shows the bonds going to the red sphere, which is an oxygen atom. The space-filling representation has them pushed closely together. That's just to indicate the fact that in reality, they're going to be really close and overlapping a little bit. I know this is water in the gas phase because it has expanded to fill its container, and there's as much space as possible between the two, or between the different particles of the gas. Different elements are represented by different colors. You need to know the first four. That the black spheres always represent carbon, the white spheres are for hydrogen, the red spheres are for oxygen, and the blue spheres are for nitrogen. We won't see these other colors hardly at all. In fact, I don't even know them. The first four are the ones I'm focused on, and I want you to recognize in these pictures. Structure of the atom. Well, we said that all matter is made up of different combinations of atoms. Atoms that themselves are made up of three main subatomic particles. Now that's as in-depth as your book gets. Of course, at this point, we now know there's other things like quarks. Isn't that a great name, quark? Those make up the two of the particles we're about to see. So there are smaller parts than these subatomic particles, meaning smaller than the atom, inside the atom. And here we go. I think it's page 42 in your textbook. It's a set of three of the main, or the largest particles that are inside an atom. One is the proton. Proton starts with the letter P. It's also being pro something, is when you're feeling good about it, supporting it. So that particular particle has a +1 charge. And whenever I ask you for the charge of something, I'm going to need two things from you, unless it's zero. I'm going to need a positive or negative, or plus or minus. I don't care, but I need positive or negative, and I need a number. Protons have a charge of +1. They also have a ridiculously tiny mass. Look at that in grams. That's 23 zeros before we finally get to the 16726. Super duper tiny. And so at this point, scientists were like, we're not going to write out that mass every single time we want to talk about the mass of a proton, or even these other guys, this neutron and electron. So they said, hey, we have the power to create a new unit, an atomic mass unit, or AMU for short. And they noticed this guy neutron, who's neutral and has 0 charge, had a very similar mass to that of the proton. See how he still also has 23 zeros before getting to the first number 1? They said, let's just go ahead and say both of those particles have an atomic mass unit of 1. And that's how we're going to refer to them. We're not going to worry about these ridiculously tiny masses. We're just going to focus on the protons having a +1 charge and a mass of 1. The neutrons having 0 charge and a mass of 1. Those teeny tiny electrons, so important when it comes to having a reaction between elements, but they, like elections, have a negative charge, a -1 charge to be exact. Their masses are 1,800 times smaller than that of the protons and neutrons. So at that point, the scientists are like, it's negligible. We give them a 0 atomic mass units because they're so much smaller than the protons and neutrons. Protons can be symbolized with a P and a plus sign. So when you're taking notes, you can make a shortcut that way. Neutrons would be an N with a 0 because they're neutral. They're about the same amount of matter, with similar extremely small masses. The electrons are even smaller, so they're assigned an atomic mass unit, AMU, of 0. Let's talk about inside an atom. There's a nucleus right in the center. Now, for those of you who may have been studying biology, you have probably heard that our cells, those of animals and plant cells, we all have nuclei inside of our cells too. The difference is that the nucleus in a cell can be anywhere inside the cell. The nucleus in an atom is only located at the center of the atom. And we know that from different experiments that have been done. Again, I'm not going to go over those in this course, but a lot of scientists have come before us and figured out a lot about the atoms. In that nucleus, we have all of our protons and neutrons. So this is a very positive center to the atom. I want to give you a feeling about the size. So for just a second, close your eyes and think about either maybe standing in the middle of a baseball stadium or even a football stadium. You're in this large stadium, okay? And you're standing in the center and you're holding something between the size of maybe a marble. Biggest I've heard it represented is a baseball. So there you are, and feel all that space around you. See all that space around you in the football stadium or baseball stadium, holding this tiny object with you at the center. Well, the tiny object, the marble or the baseball, that's the nucleus. That's where all these protons and neutrons are crammed in. This is where all the mass is. And we talked a little bit about density, right? Density is made up of the mass divided by the volume. Well, all my mass is in the nucleus, and it's a very, very tiny volume. Big number divided by a very tiny number equals a very dense nucleus. You can open your eyes again. That dense core of the atom is where all of my protons and neutrons are. It has an overall positive charge from the protons. Around the nucleus, we have what loosely is called the electron cloud. So that's the rest of the space in the stadium. The rest of the space in the stadium around you is the electron cloud. This is where electrons hang out. They're all zipping around, not with much matter to them, not with much mass, but they are flying around with their charge, each with a -1 charge. They make up most of the atom's volume. When we look at the periodic table, we can get some information from each of those squares on the table. The atomic number, which for some reason is represented by the letter Z, even though that's the last letter in the alphabet, I'm sure it's a Latin thing. Atomic number Z is the number of protons in the atom. And by the way, the reason why we have symbols like SN for tin is because in Latin it's called stanic or stannis, depending on which form it's in. So it's a Latin term. Most of the weird names that you'll find for elements, they weren't in English originally. So they have these names and symbols that are different than what we call them. All right, and so this letter Z represents the atomic number. The atomic number is the number of protons in the atom. The number of protons doesn't change when we do a chemical reaction. Every atom of a given element has the same atomic number. Li stands for lithium. That's an element, it's a metal, and every single atom of lithium has the same atomic number, number 3. Every atom of a given element has the same number of protons in its nucleus. Every atom of lithium has 3 protons. Every element has a unique atomic number. The only element with atomic number 3 is lithium. Every element has a unique number of protons. The only element with 3 protons inside its nucleus is lithium. Then, a neutral atom has no net overall charge. In that case, the number of protons, each with a positive 1 charge, must equal the number of electrons, each with a negative 1 charge. When I look at the periodic table, I'm getting information about protons and electrons and neutrons from the periodic table. And the first thing I recognize is that everybody on there is neutral. If I know the number of protons, I know the number of electrons. They'll be equal as long as we're talking about a neutral atom. All elements there are considered neutral with 0 total charge. Positive and negative cancel out. When we get to chapter 3, we'll start learning about what happens if an atom loses electrons or gains extra electrons. Then it's no longer going to be neutral. But the starting point for the number of electrons will still be based on how many protons are in the nucleus. The element chlorine, written in what we call isotope notation, there's another name for it. It's written in this format where we have the symbol for chlorine, Cl. In the bottom left-hand corner, I have a smaller number. In the top left-hand corner, I have a larger number. The bottom left-hand corner is for the atomic number. Well, what do we know about the atomic number? That always tells us the number of protons. So, how many protons does chlorine have? 17. Great. Now we're going to assume this is neutral. I have no indications that there's a charge on this atom, which means then that there are an equal number of electrons. How many electrons does this atom of chlorine have? Also 17. In fact, any atom I find anywhere with chlorine, if I call it chlorine, it's got 17 protons. And if it's neutral, it will then have 17 electrons. The mass number for a particular atom of chlorine could be 35. Do you remember which 2 particles have mass? Which ones were both an atomic mass unit of 1? Protons, neutrons, electrons, 2 of those had an atomic mass unit of 1. It was the protons and the neutrons. Remember those electrons, they're so tiny, we say they have 0 atomic mass. Well, that means that if I add up all the protons, who each have a mass of 1, plus all the neutrons, which also each have a mass of 1, I will get a total mass for that atom. And they call that the mass number. If this atom of chlorine has 17 protons, which it always will, because that's its atomic number, then we can do subtraction to figure out the number of neutrons. The mass number minus the number of protons will give us the number of neutrons. The number of neutrons is going to equal the mass number minus the number of protons. In this case, we're told that its mass is 35. Take away the 17 atomic mass units coming from the 17 protons, and we're left with 18 neutrons. Remember when I said that a particular atom of chlorine might have a mass of 35? Well, that's because elements can come in more than one version. And these different versions of the same element are known as isotopes. Iso means same. What's different about these atoms of the same element is that they have a different number of neutrons. The protons, and the electrons will still be equal as long as it's neutral, but the number of neutrons can change. The masses will also change, right? Because if each neutron has a mass of 1, and we have different numbers of neutrons, our atoms will have different masses. Most elements in nature exist as a mixture of isotopes. That chlorine 35, that's what we call that particular atom that had the 17 protons, 17 electrons, and 18 neutrons. Well, I think about, forget what it is it like maybe 55% of atoms that occur naturally have that particular mass of 35 and have 18 neutrons? There's almost an equal amount of chlorine atoms that have a mass of 37. Still 17 protons, still 17 electrons, but now it has more neutrons. It's known as chlorine and then a dash or hyphen 37. I have to tell people in the name what the atomic mass is, because the chlorine name tells me immediately how many protons there are, but I won't know which version it is until I tell people what the total mass is. How many neutrons does chlorine 37 have? So take a look at the formula. We said the number of neutrons equals what? It's going to be the mass number, which in this case, for this isotope, is 37. Then subtract the atomic number, which for chlorine is always 17. 37 minus the 17 protons leaves us with 20 neutrons. And the cool thing about different isotopes, they don't necessarily have to have big differences, but a lot of the elements have some isotopes that are radioactive, which is why we're going to cover chapter 10 next, because that has to do with radioactive materials. I don't think either one of these is radioactive. Chlorine 35 and chlorine 37, I believe, are not hazardous, but they do have differing numbers of neutrons. I can guarantee that will be a test question for how many different neutrons they have in them. So how about, see, I think I have to come up with something different to be your thing, to make sure you've at least looked at some of this and watched this. What should we say our code word will be today? Oh, I know. Maybe, I don't know if I'm ever going to say the bit about snotting again. So if you can remember the joke about snot tin, that SN is the symbol for tin, TIN, that could be our code word for watching this particular video, okay? All right. Now, writing isotope notations of elements. I want you to begin with the symbol for the element. Our symbol this time is for sodium. You can take a look at your periodic table if you want. Sodium is in the first column. His symbol is Na. Again, it's a Latin thing. Then you're going to round the mass on the periodic table to a whole number. This is if you're going to be asked to write atomic number looking at the periodic table. I think what we're going to do is I'm typically going to tell you the atomic mass. The reason why you have to take the ones on the periodic table and round them is because all the masses on the periodic table, for everything that exists long enough to get its mass, to weigh it, they all have decimals in them. So we just need a whole number version. I'll probably tell you what the atomic mass is for a particular atom. That is going to end up going in the top left corner. It's always going to be the bigger number, unless we're talking about hydrogen. In the case of hydrogen, both of his numbers will be 1. Then place the atomic number. Those are the whole numbers on the periodic table. The ones that don't have a period, a decimal, you're going to put that at the bottom left. So take a look at sodium and see which whole number goes with him. For him, it's going to be 11, right? Okay, good. This is an isotope notation. There's another word for it, but this is the term that we're going to use. I think it's a great format for finding the number of neutrons. Look how we've already got it set up for a subtraction with the bigger number on top and the numbers lined right up. 23 minus 11 tells me I've got 12 neutrons. Atomic mass minus atomic number. If I just gave you the atomic number, the 11, you should be able to go to the periodic table and figure out that that's for sodium, because he's the only element that has the atomic number 11. If I gave you the 23, that could be tricky. Thanks to these concepts of isotopes, there are different elements that can have the same atomic mass. They can exist in different forms with different numbers of neutrons. So looking up atomic mass is not a good way to find the identity of an atom. The number of protons or the atomic number, that's what you've got to look for. The atomic weight, the one that we see written on the periodic table, that's calculated from the masses of each naturally occurring isotope of an element. So they looked for all the naturally occurring isotopes, all those different atoms for each element. They figured out the individual masses for each of those atoms. Then they also took into account how much of each isotope existed in nature. For some, it might just be 100% of one particular form. There's other ones where it's 50% one form and 50% another form. Then there's some, I've seen some that had like up to 10 naturally occurring isotopes in nature. They do a mathematical calculation, what we call a weighted average. And that's why we end up with those decimal values. If I'm just talking about the mass of an atom, I'm going to be talking about atomic mass units, or AMU. On the periodic table, carbon's shown as 6 atomic number, C, the symbol for carbon, 12.01. That 12.01 is the atomic weight. It's in atomic mass units. And it is a weighted average of the different forms of carbon. The most common isotope for carbon is carbon 12. Notice how I called it carbon, and then we would have that hyphen 12 because the 12 tells me what his mass is. But the atomic weight on the periodic table is not exactly 12. Why not? Well, that's because there's a couple more forms of carbon. There's carbon 13 and carbon 14. They each have a higher mass than the most common form, carbon 12. But there's only teeny tiny amounts of them. So our mass is almost exactly 12, but a little bit off. For you to be able to calculate the number of neutrons in an atom, you're going to be given an atomic mass for that particular atom. That way you know which isotope you're working with. I'm not going to make you do any of the calculations. In fact, I purposely took them out of the Connect homework assignment, and I tried to get rid of them on the optional Connect. It may still be on there. It's possible that it's still in the optional Learn Smart thing, but it'll give you instructions for how to do it. And quite frankly, it's a very useful skill to know how to multiply a percent times a value, and then do it again for each of the other components and add them together. Okay, so now we're going to talk about the periodic table. Dmitri Mendeleev, February 8th, 1834 to February 2nd, 1907. He is credited as being the creator of the first version of the periodic table of elements. Using the table, he predicted the properties of elements yet to be discovered, and he did it correctly. He reported his findings in 1899, I believe, at the Russian Chemical Society conference. There is another scientist who came out around the same time who has a version that had similar success. However, he was not as outspoken and did not promote his version as much as Mendeleev did. So I don't even remember the person's name, but Mendeleev I know, because he's famous for taking credit for this. And it is a pretty amazing thing that he was able to do. Feel free to look into how that all came about, lining things up based on their chemical properties and knowing that something else must exist, but they don't have it yet. It's kind of cool. The periodic table up there. Every time you go across a row, left to right, that's known as a period. So imagine that, remember how class periods, first period, second period, third period, you would sit in rows of chairs. So those are your periods. The ones that we're going to use the most, so you might have a question on your homework about periods, but we're going to always talk about groups. Those are the columns, the up and down part. They are really, really, really important. The main group elements, those are the guys in the high-rise apartment, okay? So see those two blue columns on the left-hand side of the table? That's a high-rise apartment. And 6 columns on the right-hand side. That's another set of high-rise apartments. Those two sides, those are the main group elements. That big block of yellow that goes through the center, those are not main group elements. It's just the guys in the tall columns on each side. They're numbered groups 1A through 8A. Now, if you look at older periodic tables, it's going to be groups 1, 2, and then 13, 14, 15, 16, 17, 18. Even then, it's okay, though, because group 13 that has a 3 in it, that's group 3A. Group 18, well, that's group 8A. So it's not too bad if you still have an older version of the periodic table. You're going to see when we get to chapter 3, how useful it is, though, to number them 1 through 8. Those short columns in the middle, the ones that are all yellow, if you are, by the way, if you are colorblind, please let me know as soon as possible, because I can give you black and white versions of things. The transition metal elements, they help us transition from metals to nonmetals. They're in those 10 short columns in the middle, and sometimes they're numbered from 1B to 8B or 3B to 12B. I mean, it depends. We're not going to talk about the B's at all. We're just going to be focused on groups 1A through 8A. Lastly, the inner transition elements. Those are known as the lanthanides and the actinides. They are those two bottom, those long rows down there at the bottom. Technically, if you look at their atomic numbers, they belong in those white squares up with the yellow squares. However, it threw off the symmetry of the periodic table. They wanted to keep it a nice rectangle. So these are known as inner transition elements because they would squeeze into those two bottom rows of the yellow. We're not going to really deal too much with those, except that some of them are famous, especially for radioactivity, like uranium's on there, plutonium, those guys are on there. And there's some really expensive ones on there. I remember back like in the early 2010s, Californium at the time, 1 gram, so like 1/3 of the mass of a penny, 1 gram of it cost $1 million. So some of those elements, because they can only be created in the lab and they're very rare, can cost a fortune. Here we go. Elements that are in the same period, the same row on the periodic table, they are similar in size. And we're not going to get too much into detail about that, but I do want you to understand that while the ones in the same period are similar in size, each time we go to a new row, the atoms are getting larger and larger. So they're adding on more and more electrons into new areas that are going to continue to make my atom larger and larger, going down the periodic table. Elements were originally added across the rows in order of their increasing atomic weight. Now they are added in order of atomic number. It's almost the same order. It's kind of cool though. Over here, argon, AR, he's atomic number 18. His mass is 39.948. And then potassium, the K, think of like bananas have a lot of potassium in them, and special K cereal, you put your bananas on the special K cereal. So that helps me remember the letter K goes with potassium. His mass is only 39.09 instead of 94. So his atomic number is larger. His chemical properties match lithium and sodium. So he's in the right spot, but now we really see that they're in order based on their atomic number. The number of which particle? Protons. Good. Atomic numbers equal the number of protons in the atom, always, always. New rows, as they made the periodic table, were created to line up elements with similar electronic, meaning based on the number of electrons they had, and chemical properties, putting them all in the same column, the same up and down group. So this is a common thing I'll ask you about. What elements, say in group 2A there, group 2A, you should know that beryllium, the Be, magnesium, Mg, and calcium, Ca, these guys all have similar chemical properties. Do you remember what that means? It means that if I put them with other elements, say oxygen, or I put them in water, they're going to react in a similar way as the ones above and below them. Okay, so reinforcing that. So let's talk about group numbers. Group 1A, not hydrogen, but the other guys in group 1A, such as lithium, sodium, potassium, these are known as alkali metals. Alkali means basic. The ones next door in group 2A are known as alkaline earth elements, or sometimes alkaline earth metals. All of these are soft and shiny metals. We could take a sharp knife and cut through them, and they are very shiny. They have high luster. Remember luster? They're lustrous. They also have low melting points, so it wouldn't take a lot of heat to make them melt into a liquid. They're your typical metals that are good conductors of heat and electricity. One way that helps me remember that the alkali metals are group 1, whereas the 2-word alkaline earth is group 2A. 1 word for alkali, that's 1A. 2 words, alkaline earth, that's 2A. Both of these groups of elements react with water to form basic solutions, meaning the opposite of acidic. They're going to be basic. And we'll learn more about this when we get to chapter 9 that has to do with acids and bases. Oh, we get to watch a video. Oh boy. I have to do something with my, you know what, you're not going to want to watch it with me because my computer does something really weird. What I need you guys to do then, I know, I'll put the link to this video on Moodle, or if you end up opening up this PowerPoint, if you're in the slideshow mode, which I highly recommend when you go through PowerPoint so you don't get everything all at once, you'll just be able to left click on that and it'll open it up in YouTube for the video. If you're not watching it in slideshow and just come straight to this, in PowerPoint, you left click or hold down the control button and then left click. It might be different on the, what are those things called? Macs. Mine's a control button. Okay, yours might be the command button. It's a fun video. I'd love to watch it with you. I'm sorry my computer will make it all choppy and it won't be fun. Okay, I might watch it another time with you. I like things that blow up, so I do try to find videos that blow things up. Group 7A. These name for these guys is halogens. I want you to know, I need you to memorize that because I'll talk about halogens a lot. And I don't want you to be confused about who I'm talking about. These are the guys on the second to last row or last column. So it's fluorine, chlorine, bromine, iodine. Those are all my halogens. They exist in nature as two atoms joined together. And I mentioned this during our first session, our first live session. There's 7 elements actually that exist as two atoms joined together in nature. These halogens are very reactive, which is why I end up talking about them a lot with you, because they do love to react with a lot of things. They will combine with many other elements to form compounds. We're going to see them both reacting with metals and with other nonmetals or metalloids. Lots of different things will have these halogens in them. Oh, it's another fun video. Okay, I'll resist. Please watch the video. It's fun. Things explode. Okay. And lastly, our noble gases. Now those guys, they're kind of cool, and hopefully I have that slide next, but they're the opposite of halogens. Even though they're their neighbors next door, the noble gases are very stable. In fact, we're going to learn that everybody likes to be like them. So make sure you know that the last column on the periodic table, group 8A or 18, if you have an older periodic table, those are your noble gases. And other elements, their goal is to be like the noble gases. So we'll talk about those a lot. It's helium that goes in balloons and makes your voice go really high. And neon, like neon lights. Argon is also something that makes what we call neon lights glow. And krypton, of course, where Superman was born. And xenon is on there as well. I feel like I'm forgetting somebody. The deal with the noble gases is they rarely combine with any other elements. I know you can't see all the way back there, but if you look on your periodic table, definitely the top 2. Recently, I think I saw something where the third one down reacts, but definitely helium and neon. Scientists haven't found any compounds that contain those 2 atoms yet, those 2 elements. So helium atoms just stay by themselves. They don't even join together with each other. Neon atoms, they don't react with any other element, and they don't join 2 atoms together either. They are completely unreactive. They have been able to make some compounds between the next 3, argon, krypton, and xenon. There are maybe 1 or 2 compounds made with those elements, and fluorine. Fluorine is the top halogen next door, atomic number 9. And fluorine is so reactive. He's a gas and at room temperature. And he's so reactive that even things like glass and water will burn in the presence of fluorine. So I think of oxygen lots of times as being super reactive, and things catch on fire when they're around oxygen and things, but fluorine, everything burns in the presence of fluorine. Exciting guy. And that's why they're able, under really, really, really harsh conditions, they can make a couple of compounds between the noble gases and fluorine. But that's all I've seen so far. Very unreactive, very stable elements. Oh, goody, I did have a pretty picture. The noble gases glow when they're electrified. And so we can get mixtures of gases to create different colors, or just certain pure gases of these different ones. And you put electricity through them, and they release energy in the form of these different colored lights. Where are electrons located? I told you that they're in the stadium, right? That we have our protons and neutrons in the tiny ball at the center of the stadium. The electrons are everywhere else, and I told you they're zipping around, but technically they don't get to go just anywhere. They are not moving completely freely. In fact, the electrons are confined to specific regions, and each of those regions give it a certain amount of energy. The energy depends on how close they are to those cute little protons. The energy levels or regions are known as shells. So you may hear me talking about shells, not like seashore shells, but more rings of energy. And the electrons hang out there. Now, they stay in an atom just because they're attracted to the protons. You may have heard opposites attract. So I think of the protons in the nucleus as being on stage. And the electrons, they come to watch the show. And they'll sit in rings of chairs around the stage that has those cute protons on it. And they're all coming to see the protons do their thing, and they're attracted to them. But there's a certain number of seats in each row. Those rows of seats, those are known as shells, and they each have a different level of energy to them. We number the shells 1, 2, 3, so on. Electrons that are in the lower numbered shells, so the ones closest to the nucleus, closest to the protons that they're attracted to, they are the lowest in energy. I imagine them getting front row seats, just sitting there going, oh yeah, there is nowhere else I'd rather be right now. Just really low energy and mellow sitting there, right? Electrons fill in, but there's not a lot of seats close to the stage. So as electrons start filling in the seats more and more, they start having to go to rows that are farther and farther away from the stage. And in that case, they start getting kind of antsy. They're like, well, should I stay here? Should I go somewhere else to another atom? Maybe I could have a closer seat to their stage. Or maybe I'm going to invite some friends over and maybe I'll go hang out at their place sometimes. Sometimes they'll hang out over here. So as I get farther and farther from the nucleus, where the protons are, my electrons start being in higher energy levels. They're more anxious, not sure whether to stay or whether to go. Higher energy electrons, the farther they are from the nucleus where the protons are. Oh, goody, it's a new one. So what does it say? The study of electrons, we have these different shapes in the particle physics lab, and it says, I don't know about you, Jerry, but I'm feeling a lot of negative energy in this room because electrons have a negative charge. So yeah, this representation you see right there, that's pretty common to show the protons as a positive charge in the center, in the nucleus, and then the electrons, they're filling in those rows of seats around the stage, around the nucleus. But you can tell, as my rings get bigger, going away from it, there's more room for more electrons. Close to the stage, there's actually only 2 front row seats. And then there's only 8 second row seats. Then we start having more and more. We've got 18 third row seats and so forth, but it's pretty competitive getting those low energy seats. And as we get to the outermost shell, so the energy level that's the farthest away from the nucleus, it gets a special name. It's known as the valence shell. When I take a look at the periodic table and I find an element, whatever row he's in, that is a clue. It's a shortcut for me to know what valence shell he's in. The chemical properties of an element depend on the most loosely held electrons, the ones that are found in the valence shell. Again, the guys that are farthest from the stage with the protons are the ones that are the most antsy, high energy. They're debating whether to stay, whether to go, or whether to invite friends over for a while. They're the ones that are going to be involved in bonding and doing chemical reactions. They're known as valence electrons. I'm going to talk about valence electrons a lot, so I need you to know electrons involved in bonding are valence electrons. Electrons involved in bonding are valence electrons. And remember, it's the bonding that occurs during a chemical reaction. That's when I can take 2 atoms, either of the same element or different elements. They join together, and the joining together involves the valence electrons. A shortcut. I love those shortcuts. The shortcut for determining the number of valence electrons, if they're in the high-rise apartments, groups 1A through 8A. the main group elements. Their number of valence electrons equals their group number. The only exception to that is helium. If you take a look at helium, look on your periodic table. I can see it way back there, but I don't think you can. His atomic number is 2. So even though helium, a noble gas, is in group 8A, he only has 2 electrons. He has 2 valence electrons because in his case, those 2 electrons, they've got those front row seats. And so his energy level farthest from the stage is just the front row seats. So he's got 2 valence electrons. But after him, everybody else in group 8A has 8 valence electrons. Everyone in group 1A has 1 valence electron. We're going to talk about those all the time. So I need you to know this shortcut, and I need you to know that the valence electrons are involved in bonding. All those other electrons in them are called core electrons, and they don't really go anywhere. They just hang out. Most transition metals, do you remember where those are? They're those yellow rows there in the center that help us transition from metals to nonmetals and metalloids. Those transition metals have 2 valence electrons. Not all of them, but most of them do. And remember, for everybody, their valence shell is whatever row number they're in. Currently, our periodic tables go from row 1 down to row 7. And my shower curtain is outdated. It only goes up to element 111, but thanks to advances in scientific techniques and stuff, we now are aware of elements all the way up to 118. And so I'm really excited because we're going to start ending up now with new levels and new rows on the periodic table, all kinds of cool stuff. So I'm excited to find out who element 119 is going to be. End of slideshow. So now's my opportunity to show you another geeky part of me. And that, if I escape this, I can do a new share and do the other camera and show you my geeky bracelet. I bought some stuff just to make it more interesting when we were in lab and everything. And here's my geeky periodic table of elements. Back when, right before actually, the pandemic shut down a lot of stuff, I went to the really, really great science museum in Raleigh. When we're able to go out in public again and it's safe, I highly recommend the Museum of Natural Sciences in downtown Raleigh. And this was, I could spend half my time just in their gift shop, but this was in their gift shop. And later, you'll sometimes see me with an organic model of caffeine. I'll wear it on my necklace. But that's my really nifty periodic table bracelet that I got to, I don't know, it's my way of looking cool to you guys, because I'm sure you think I'm really cool after knowing I have that. What was missing in this? The math, right? We did one subtraction thing to find the number of neutrons, and that was it. So that's pretty cool that you don't have to do all the unit conversion stuff that we saw in chapter 1. That should give some of you some more time to practice with the chapter 1 concepts. And we'll do a little bit of unit conversion in chapter 10, but not a whole lot. I'm just going to need you to convert between things like, what will I make you convert between? We need millicuries, milliliters, that's it. Milliliters and millicuries will come up. Okay. I don't think I have anything else to show you guys now though. So I hope you enjoyed this recording, and hopefully you were listening in when I said what would be the code information, which I'm going to have to write down. Oh yeah, it was a trick for memorizing the symbol for one of the elements. So keep an ear out for that. And better yet, come to my live sessions, ask some questions, participate, and it won't matter if you picked up on the code word from this video or not. I'll see you soon, I hope. and I'll be putting up some homework assignments, probably just one for now, on Connect. Take care. Thanks for watching.